So, we will continue our discussion. So, this based on the free electron gas model, so we have seen that when we will apply electric field, so that will be the acceleration of the electron and relaxation time in terms of mean free path, that is on another relation. Now, this velocity is basically this velocity, and after applying before applying electric field, this is the velocity, right. So, from kinetic theory one can get the velocity, that depends on the temperature, and then velocity after applying electric field. So, that is called drift velocity. So, it is along the direction of the electric field. So, that is v dash v bar. So, drift velocity v bar equal to s by tau. So, s equal to half a tau square and this by tau, so is tau, right. Now, if I put value of a, so I will get half a is E by m and tau is lambda by v, right. So, this is the drift velocity. Here charge, mass, electric field and lambda is mean free path. Now, v one can find from here. So, what is the v? So, if I replace v half E by m, this lambda let me write here. So, 1 by v so its v square is there. So, if I write 1 v here, then v square. So, 1 by v square I will replace. So, 1 v will be there and this v square is basically we will get 1 by v square. So, 1 by v square I will get half m 2 by 3 k b t, right. Sorry, it has to be 3 k b t, right. So, what we are getting? We are getting this m, then this 2 will go. So, 6 we are getting 6 k b t e lambda v. Okay, so that is the that is the drift velocity of electrons under electric field. So, now we can define the current in terms of known parameter. So, current density J. What is current density? What is current? Current, we define that per unit time number of electron passing through a cross sectional area A. Okay. So, that will be the current. So, current density is just per unit area, per unit cross sectional area. Okay. So, this current density one can write, I have to see if this is the conductor, right. If I take this cross section, right. Now, per unit time at t equal to per unit time t equal to 1, how many charge will move? So, if charge density n is charge density, number of electrons per unit volume, right. Now, in once if velocity is v bar, so velocity is nothing but the distance traversed by a unit time, right, per second. So, that means this length, it will traverse this length unit time, this length is v bar, right, because this length it is traversed by 1 second. So, in 1 second this the length traversed by the electron, and now this cross section, if it is 1 per unit cross section, if I take unit cross section, this one. So, this will be the volume, So, volume will be this into cross section, this is the velocity, but it is now length for per unit time and cross section A. So, length into this cross section, that will be the volume. So, that basically this is the volume. So, V bar will be the volume, right, and in that volume, if volume density is n, number density of electron is n. So, how many electron will be in this volume? N V bar, and so this many number of electrons will be in this volume. So, into charge is E for 1 electron. So, total charge is this. So, this much charge is passing through a cross section, unit cross section per unit time. So, that is defined as a it is defined as a charge density, right. It is defined as charge density. So, to get this charge density, so this N, this E, and that V bar, we have got this V bar is this. So, one can write E is here. So, I will write E square lambda V by 6 kBT into this E. Okay. So, its current density, I was telling charge density. So, charge density is N, this is the current density. So, this is now expression from where I can see that N for a particular material, N is constant, these all are constant, and this lambda, this V. Okay. So, this its lambda is it will depend on the that material, which metal we have taken, right. So, temperature for a particular temperature is constant. So, here I can write that J is proportional to E when T is constant, when T is T constant and metal is constant, means for a particular metal, for a particular temperature, for a particular metal, other parameter depends on that metal, except T, other parameter depends on that metal, right, that electron density, mean free path, its kinetic velocity, basically Maxwell velocity. Okay. And yeah. So, it depends on temperature. So, when temperature is constant, so that is fine. So, these are constant. So, under this condition, this is very important, I emphasized on this point, that under this condition J is proportional to E, current density is proportional to electric field, right. So, this is nothing but Ohm's law. This is nothing but Ohm's law. Okay. So, all metals obey Ohm's law, and that generally without knowing in details we use for our electrical circuit, right, to study the electrical property, just we use. But why it behaves like this, why current density is proportional to electric field, or current is proportional to V, right, this potential. So, we are familiar with this form, generally we are familiar with this form. So, why it is like this? So, that origin of this relation, now we can see it is because of the free electron available in the metal. Okay. So, we could derive this one, and you know the relation of current density and current. So, to get current density, to get current from current density, one has to multiply with the cross sectional area. So, current is through a rod, through a metal. Okay. The charge will pass through that rod, means through the whole cross section per unit time. So, that is the current, and current density, just current density is basically, the current density is nothing but current by cross sectional area, right. So, it is basically for a particular material, so it is not enough it is not enough when we express in terms of current. When we express in terms of current, so we have to tell that for a, it is not only for a particular material, but for a particular geometry of that material also, that is important. So, then it will, if I talk in terms of current, so it will depend on the geometry of the metal, but if I talk in terms of current density, so it will be independent of the geometry of the metal. So, that is why it is more general parameter than the current. Okay. And voltage also, what is the relation? Voltage V is basically, it is related to the electric field, V by D, right. What is D? D is the, if you have applied voltage, across these two surfaces, then electric field in this between this length, it will be this voltage and that separation D. So, then you will get electric field. Okay. So, now electric field is the voltage per unit length. Okay. So, then again electric field is more general term than the voltage, potential difference. Okay. So, this is basically potential gradient, electric field is basically potential gradient. So, this V by D. So, then fine. So, if I multiply with A in both sides, if I multiply with A, so then this will be current, this will be current, right. Here A term will come, this will be current, and electric field, if I multiply with D or L, if I take say L, okay. If I take L, okay. So, E can be replaced by V by L, right. Okay. So, then I can write L here. Now, this will be the constant, because here this will be constant, right, for a particular temperature, for a particular metal, and for a particular geometry of that metal. So, then here I can write that I is proportional to V, right. So, we are familiar with this form. So, this Ohm's law, and what is the proportionality constant? So, this will be the proportionality constant, and this proportionality constant will be 1 by R, right. If I write this some constant, okay. So, I can write I equal to V, some constant I have to write. So, I can R is a constant. So, 1 by R I can write for my convenience. So, this R is called the resistance, 1 by R it will be conductance, right. So, 1 by R will be conductance. So, R equal to, from here you can, so just I have to inverse it. So, 6 kb T L by n square lambda v, right. So, this we can write, and if I take this as a rho L by A, this rho is called the resistivity, this rho is called the resistivity. So, R is resistance and rho is resistivity, right, rho is resistivity. Right. So, rho is basically resistance per unit length and per unit cross section, right. So, this, and if you see this, if I have included A and L, right, when I consider the J. So, if you just leave this A and L, so whatever this term will be there. So, this here I have taken inverse 1 by R, but if I do not take inverse. So, this, so J equal to sigma E, the sigma, that sigma will be, sigma is called conductivity and it will be just 1 by rho, it will be just 1 by rho. Okay. So, before putting this A and L, whatever things was there. So, if you check, just it will be inverse of this one. So, it is one can see, right. So, from free electron model we could explain microscopically that why metal follows the Ohm's law, and from there everything we got. Now what is the parameters on which this resistivity or conductivity depends, right. So, definitely it depends on the mainly it depends on the electron density in that metal. So, metal to metal it varies the conductivity, mainly this electron density is responsible. If you keep other parameter for, if you study for same temperature and etc. Okay. So, this is one part we could derive from the free electron model. So, here I will I think I can use this part. Now, this so there I showed you that I think it is temperature, conductivity. So, resistivity as I told, it is proportional to T. If you think about the temperature, so resistivity I have written, that is the resistivity. So, resistivity is basically proportional to T, right. It is a room temperature, at room temperature. So, it follows resistivity follows, so it is proportional to temperature T, and that also one can see from here, right. And yes, Next, if I want to see this k by that Wiedemann-Franz law, k by sigma is proportional to T Wiedemann-Franz law. If I want to prove it, so I need this sigma expression. So, sigma is n e square lambda v by 6 k b t, right. So, then I can this expression, okay. So, for thermal conductivity, what is thermal conductivity? It is just similar to electrical conductivity. So, in case of electrical conductivity, if you apply electrical potential difference, and then charge flows, it goes from one place to another place. So, when it is going, so what is the velocity of that of the electrons, okay, and what is the electron density of that material. So, depending on that, this conductivity is decided. Similarly, for thermal conductivity, for thermal conduction, this we have to apply temperature difference. Now, this the amount of current, earlier in case of electrical amount of we express amount of charge or amount of this current flows through that potential difference. So, here amount of heat, thermal heat, it transfer from one temperature to another temperature. Okay. So, how fast it moves, or what is the resistance of this passing this heat from one place to another place. So, that we express in terms of thermal conductivity, right. So, from kinetic theory of using kinetic theory of gas, one can one can find out that quantity of heat passing through a cross section of a rod per unit area and per unit time. So, that is similar, okay, per unit area and per unit time amount of charge passing through the potential gradient. So, that was the charge density, right, current density. So, here also definition is similar. So, amount of charge. So, from kinetic theory, applying kinetic theory, because this in case of free model of electron gas. So, this one can apply kinetic theory, and applying kinetic theory one can get the expression. I will not derive that one. So, I will just take that one. So, that is basically 1/3 n v lambda dE by dL. Okay. So, this is the density, electron density or gas density in case of gas. So, gas density, here electron density, electron gas, electron density, V is the velocity, okay, whatever velocity we have seen earlier. So, that is the velocity, and lambda mean free path, and dE by dl. So, dE is the kinetic energy, E is the kinetic energy of the is the kinetic energy of this electrons, and this change of kinetic energy when it is passing through this length dl length. Okay. So, this E, what is the kinetic energy E? That is 3 by 2 kBT, right. So, dE by dl, it will be 3 by 2 k dt by dl. So, how much energy transferred, heat energy transferred from one end to the other end where temperature difference is applied. Okay. So, from kinetic theory one can find out this the amount of heat will transfer. Okay. So, then this I can replace with dl, right. So, this will give me half n v lambda. This is, let me write kb, earlier I have used kb. So, it is kb, okay, dt by dl. Okay. So, this amount of so this now this one can write is a constant, it is a constant term for a particular metal. Okay. So, this per unit time, we have to remember this, we have defined per unit time, per unit cross section. It is similar to similar to this J, it is similar to J, you know, it is similar to J, current density. Okay. So, this K is called thermal conductivity, this K is called thermal conductivity. Okay. Now, if you find K by sigma or sigma by k, let me write sigma by k because already sigma is there. So, by k means into 2 by I do not know whether I can go out of the yes. So, okay, keep it sigma. Now, here I will use that, this is the better place. So, K by sigma ratio of thermal conductivity and electrical conductivity. So, this is N V lambda K B divided by 2 by sigma 6 K B T by N square lambda V, right. So, I will get 3. So, what I am getting, N will go, V will go, lambda will go, and yes, I am getting 3 K B by E square into T, right, into T. So, So, obviously, this is that K B by sigma, it is proportional to T, and this proportionality constant is 3 K B by E whole square, right. So, that is the Wiedemann-Franz law. Wiedemann-Franz law, as I mentioned. So, from the model, free electron gas model, applying kinetic theory, one can get the proof of laws which are experimentally verified. So, free electron model is very successful model to explain Ohm's law, to explain Wiedemann-Franz law, but it has drawbacks also. It cannot explain everything. It cannot explain the magnetic susceptibility, magnetic susceptibility of metal. This model cannot explain. It cannot explain this why this mean free path for metal is very high. Okay. So, it can one electron can go the path of 10 to the power say 9 times of the lattice constant. Okay. So, why it is so transparent to electron, metal is so transparent to electron. So, it can travel a very long distance, maybe few centimeters without collision. Okay. So, why it so free electron model cannot explain them. So, this model is quite successful for some cases, but it has drawbacks. So, reason is that there is a difference of between the free electron gas and the gas, atomic gas, okay, because these are charged particle and these are neutral particle for gas, okay. And charged particle here, whatever distribution we have used, they have used as a Maxwell-Boltzmann statistics is used. So, that is good for the gas, neutral gas, but that is not applicable to the it is not applicable to the electron gas, because electron is charged particle. Okay. It's called fermion. Okay. So, for that this appropriate statistics is Fermi-Dirac statistics. One has to use Fermi-Dirac statistics instead of Maxwell-Boltzmann statistics. So, we have to go further to get the correct pictures of metal in term for explaining the electrical or electronic properties of solid. So, we will continue in next class. So, let me stop here. Thank you for your attention.